Welcome to lesson 7.5, the SSA condition and HL congruence. So there's obviously two different key ideas we're looking at here. One would be the side-side angle condition, and the other is the hypotenuse leg congruence theorem. So to start with, we are looking at the side-side angle condition in these first two paragraphs. So as it starts, examine the triangles at the right. There are two pairs of congruent sides, AB and XY, as well as BC and YZ. Also, there is a pair of congruent, non-included angles, A and X. So that's a key that they are non-included angles, meaning they are not the ones that form the vertex of the two known sides. Now, as it states, clearly those two triangles, however, are not congruent. So in general, simply having a side-side angle condition does not guarantee congruence to triangles. So that's important to keep in mind. We do not have a strict theorem known as the side-side angle theorem of congruence because of this side-side angle condition. However, at times, the side-side angle condition does determine a unique triangle, meaning for the side-side angle condition to determine a unique triangle all of the time, there's a couple conditions that must be met. This would be listed right here. The length of the side opposite the given angle must be longer than the other given side. So again, that's the length of the side opposite the given angle must be longer than the other given side. If we meet that criteria, then that theorem is known as the SSA congruence theorem, but as you notice, the middle S is lowercase. The reason they write it that way is to emphasize that the longer side, which is the large uppercase S, is opposite the given angle. So they have those on the opposite ends of the theorem with the smaller side in the middle. That's what that theorem stands for. So the side-side angle condition can be a congruence theorem if this piece right here is met. The length of the side opposite the given angle must be longer than the other given side. So if we look at an example of that theorem, and it's stated right here in this box, if two sides and the angle opposite the longer of the two sides in one triangle are congruent respectively to two sides and the corresponding angle in another triangle, then the triangles are congruent. So that would be looking at triangles ABC and YZX over here at the right. In order to know that these are satisfying the SSA congruence theorem, we have to have this key information in which side AC is larger than BC and side YX is larger or longer than side XZ. Now, the more common and more simple of the two theorems today is the hypotenuse leg congruence theorem. Now, what you want to keep in mind is that hypotenuse leg congruence theorem only works if we have right triangles. If we don't know it's a right triangle, then we cannot use this theorem. So remember, in a right triangle, the hypotenuse is the side opposite the 90-degree angle, and the legs are the two sides adjacent to or that make up the 90-degree angle. So your longest side, always opposite 90 degrees, is the hypotenuse. So what this theorem says is if in two right triangles, the hypotenuse and the leg of one are congruent to the hypotenuse and a leg of the other, then the two triangles are congruent. Now, what you should think about and kind of notice is the hypotenuse leg theorem is a special condition, a special scenario based on this side-side angle congruence theorem, because in a right triangle, we always know the 90-degree angle, and the side opposite, the hypotenuse, is always the largest side. So in that case, this hypotenuse leg congruence theorem is actually based on this idea of side-side angle congruence theorem. So we have three examples to look at today. First example is kind of a logical verbal proof. The other two are more T-chart standard justification conclusion proofs. So in this example one, they told us segment AB represents a vertical radio tower. Now the key word in there is vertical. And in math, if something's vertical, that implies that wherever it meets the ground, it is a 90-degree angle. They want us to explain why the guy wires AC and AD of the same length, which is another key piece of info, so we know AC and AD are congruent, will reach the ground at the same distance from B. So really what we're trying to prove is that that distance from B to C is the same distance as B to D. So right away what I marked in my triangle is I knew AC was congruent to AD, and I knew my right angles. So just kind of going through the steps here, I laid them out kind of 5 different steps rather than sentences. So the first thing, if we look at triangles ABC and ABD, we know that tower AB is congruent to itself by the reflexive property. So I went in and marked AB being congruent to itself. From the given info, we knew AC was the same length as AD, so mark those as congruent. And then we knew angle ABC and ABD are 90-degree right angles because of that term vertical when describing the tower. Now I could say triangle ABC is congruent to triangle ABD by the hypotenuse leg congruence theorem. Once I've established the triangles are congruent, then we know all corresponding parts are congruent. So segment BC is congruent to segment BD by the corresponding parts of congruent figures theorem. Example 2, they gave us the information of circle A with a diameter of segment BC and that segment CE is congruent to segment BD. They want us to prove CD is parallel to EB. Now in this proof, obviously, they filled in a lot of info. We just had to fill in some of the blanks. So the first conclusion was circle A, which our justification was given. Then angles D and E are right angles. And our justification there is if an angle is inscribed in a semicircle, then it is a right angle. Coming from the idea of inscribed angles making half the measure of their opposite. So if that's a 180-degree arc, that inscribed angle would be half of that. So half the measure of a 180-degree arc is 90 degrees. Then for step 3, they said triangle CDB and triangle BEC are right triangles because they have a right angle. That's the definition of a right triangle. Saying the segment CB is congruent to BC, same segment, so that's the reflexive property of congruence. Then back to the given info of CE being congruent to BD. Now, based on steps 2, 4, and 5 in this proof, I can say triangle CDB is congruent to BEC by the hypotenuse leg congruence theorem. Then, because we have congruent triangles, we know angle DCB is congruent to angle EBC by the CP-CF theorem. And then angles B and C are alternate interior angles to CD and EB. So if alternate interior angles are congruent, then CD is parallel to EB by the alternate interior angle theorem. And our final example for today is example 3, where they gave us the info that side AB was parallel to CD, side AD was congruent to CB, and AB was congruent to CD. They also told us the measure of angle ACD was 90 degrees. They would like to prove BC is parallel to DA. So you can see in the diagram, the given info was already marked. Remember, the little arrows on segments mean parallel. So again, we need to fill in the missing parts of the proof. Measure of ACD equals 90 was given, as well as AB parallel to CD. Then the measure of CAB equals 90 is based on that idea of the perpendicular to parallels theorem, not a very commonly used one. Might even be the first time we've used it this year in a proof. Then we have angle ACD congruent and angle CAB are right angles. That comes from the definition of right angles. If their measures are 90, then by definition they are right angles. Then in step 5, they again split up the given. So step 5 was part of our given. Then when we look at our information based on the right angles and the segments, we can use the hypotenuse leg congruence theorem from steps 4 and 5 to state that triangle CAD is congruent to triangle ACB above. Once we've established the congruent triangles, we can say any of the corresponding parts are congruent. So in step 7, angle CAD is congruent to ACB by the corresponding parts of congruent figure theorem. And then our last piece, because we now state those angles are congruent, those are alternate interior angles to sides BC and DA. So BC is parallel to DA by the alternate interior angles theorem.